So, so everything started with the crystallography using this X-ray. They started with this Max von Laue. So he found this using X-ray tube with the crystal. He could see diffraction pattern on a photographic film, right? So that's where everything started. So why do we use X-ray to probe crystals? That's because of the wavelength of that X-ray is exactly the dimensions of the atoms, right? Typically we are talking about angstroms, right? 10 to the power minus 10 meters. So X-rays have wavelengths in that order. So that's why, because if your wavelength is much larger, you cannot probe the properties here, right? So with the X-rays having wavelength in that order, so we can actually not only X-rays even, so we talk about wave particle duality, right? Electrons particle. These are just, X-rays are, we call the electromagnetic waves. But the electrons, they are also particles, but you can consider that also as a wave, right? So they also have wavelengths in this order. So actually electron also can be used to probe atomic structures because they have same order. Can you use light to probe atomic features? No, because light has wavelength of 200, 300 nanometers, right? That's way bigger. So
is that the diffraction limit?
yeah, so if you have your light wavelength is something like that, right, compared to atomic, so you cannot use. So that's why X-rays and also neutrons also can be used to probe this atomic features. So that's why X-ray diffraction, electron diffraction, or neutron diffraction, I think they are, all three are pretty much complementary. So but you can see they have some different properties. Like I said, if you use X-rays, X-rays are electromagnetic waves. What is the energy? It's basically h nu, right? Or hc over lambda. So if you calculate, we know the Planck constant, we know the speed of light. If you know the wavelength, you can calculate your energies. Use this is about 1 angstrom. This means 10 to the power minus 10 meters. If you plug in, you get energies of kilo electron volts, pretty high energies, right? So electrons, X-rays have very high energies, like 12,000, right? Electron volts. So also electron volt is a big energy, right? Just remember, like, if you consider electrons, like I said, electron also we can consider as wave, right? So what wavelength do we call? It's a de Broglie wavelength, right? So usually we write your momentum given by h over lambda, right? So that these are de Broglie wavelengths. So also you can write this on h cross k, right? So the same thing. Since it is a massive particle, you can write your kinetic energy as half m v square, because you have mass, right? So but X-rays you don't have mass, right? So also you can write this one as p squared over 2m, because p is basically momentum is m times v, because we know that momentum here. From here you can calculate your energy in terms of wavelength. So p you can write as h squared over lambda squared, then you have 2m here, right? So that is the energy of electron. So we know the mass of electron. Anybody remember? Typical 10 to the power minus 27 kilograms, right? So typically electron has, for electron has minus 31, proton has minus 27, right? Yeah. So 9.1. Now plugging these numbers, we know h, we know m. If you consider your lambda to be about 1 angstrom, then your energies are only electron volts, right? It's not kilo electron volts. So electrons have much lower energies compared to X-rays. So there we were at 1/10 of X-ray energy. So same thing if you use neutron also same. This massive particle, right? As mass, you use the same thing. Only difference is what? neutron has much higher mass compared to electron, right? 10 to the power minus 27 kilograms. So that means if you plug in this one, you will see your mass is now much smaller than, much larger, right? So that means your energy is going to be much smaller. Neutrons have very low energies, right? So that has a lot of, I think, advantages. So this will not damage your sample compared to electrons or X-rays. So what I will talk about why neutrons are important for many other aspects. So please remember, electrons and neutrons, they both have masses, right? So now if you consider typical like X-ray diffraction, here is some diffraction pattern here. You can see these dots, right? Actually, if you are an expert in crystallography, by looking at that, the diffractogram, you can tell what kind of crystal symmetry you have. So this is something coming from this yttrium aluminum oxide. So the reason is the diffraction pattern tells you the symmetry of your crystal. Suppose you have a cubic crystal or rhombohedral or hexagonal. So you see some relevance with the symmetry of this pattern to the crystal symmetry. If you get this one, can you make some, later we are going to do this one. Here what can you see here? So this is C-axis is perpendicular to this one. If you look at here, this spacing and this spacing, what do you think? Are they same or different? This is different, right? This is shorter compared to this one, but they all are 90 degrees, right? So that means, can you make some guess what kind of crystal is this? It cannot be cubic, right? If it is cubic, they both should be the same. No, if hexagonal, then you need to have like 90 degree, like six-fold symmetry. Actually, this is rhombohedral. Sorry, it can be tetragonal or orthorhombic, because orthorhombic is 90 degrees, right? Actually, this structure is orthorhombic. Orthorhombic means your ABC all are different, right? So, but all 90 degrees. So, later we will do some thing. So this just to show you. Important thing is symmetry of your crystal can be seen in your diffraction. So if I see something like this kind of thing, you will see some six-fold symmetry, right? This mostly coming from like hexagonal structures, even graphene, right? Okay, so like I said, there are three kind of this diffraction studies. We can do these two here, right, at your field, but neutron diffraction you cannot do here. If you want to use diffraction, usually we go to Oak Ridge National Lab. They have this spallation neutron source, so it's not difficult. You have to write a small user proposal. So that's the DOE lab, right? So they are looking for collaborations. Then you just have some time allocated for you, you just go there. It's only little over 2-hour drive, right, to Oak Ridge, so to do any diffraction. But these two you can easily do here. We have several X-ray, so you guys are doing all the X-rays, right? And also electron diffraction also. We have a TEM, SEM to do the electron diffraction. So if you consider X-ray, what are the important characteristics? These energies are typically kilo electron volts, right? That means they have much higher penetration depth, right? It can go deep into the sample. That's why X-rays are good to look at 3D crystals. You can look at the 3D features. So then also this scattering happens from the, so typically what happens is if you have atom, right? You have neutron in the nucleus, then you have all these, I have it here. So electrons, you have these co-electrons, then you have valence electrons, all these. If X-rays come in like this, they get scattered from these electrons, right? So if you have more electrons, you get more scattering. That means if the X-rays work very good for, we call the high C material. If your atomic number is large, your X-ray works much better. For high C, you get better X-ray results. Electron, what's the situation? Remember, X-ray has much lower energy, right? That means your penetration depth is much smaller. That means electrons cannot go deep into the system. So electron diffraction is good to study mostly the surface properties because they don't go deep into this one. So mostly low penetration depth, good for surface. So neutron also has much lower energy, but important thing is this one has charge, right? So negative charge. So if you have this negative charge, electron come in, this also negative, so they also getting repelled, right? So that means you don't have much interaction with the material. But if you have neutron, what happens? It's a neutral particle, right? So, but only important thing is neutron has we call it magnetic moment. So we are going to talk about that one. So neutron has electron also has a magnetic moment, right? Because of the spinning properties. So because of this magnetic moment, so they can be useful to study mostly your sample that has some magnetic moments. They can interact with this neutron, right? That's why if you are working on magnetic materials, so neutron is a very good probe to study property because the magnetic moments in your system, they have some spins, right? Up spins, down spins. They can easily interact with the neutron magnetic moment. So then also since they don't interact with this electron because this is neutral now, right? Neutral. So they are not basically interacting with these things. That means neutron works better for low C material. X-rays work better for high C material, right? So because they are going to get scattered from this one. Another important thing is the neutrons. So you can see mostly inelastic scattering. Typically in this class, mostly we are going to talk about elastic scattering. That means your energy or your wave vector, this one and this one, the magnitudes are the same, only direction changes, right? That we call the energy is conserved, right? So that's the elastic. But neutron carrying this magnetic moment, when they interact with, suppose next chapter is about something called the phonons, lattice vibrations, right? When they interact with these phonons, so you have some loss of your energy. So that we call inelastic scattering. So the neutrons are very important to study inelastic scattering because they interact with something called the phonon. That's the next chapter we are talking about. Because so far we are talking about lattice with these, your atoms in the lattice are in equilibrium, right? But ideally that's not the case. If for any temperature higher than 0, these are always vibrating, right? So that's what we call a phonon. That's what we are going to talk about next. But at this point we are only talking about some stationary or rest atoms. So remember, these neutrons are good to study inelastic scattering as well as magnetic interactions. Okay. So typically if you look at X-rays mostly, so we can use either monochromatic X-ray. Monochromatic means that that's just one wavelength, right? Or you can use many lambda 1, lambda 2, lambda 3 different wavelengths. So here I can talk about radiation of monochromatic and this is a polychromatic. That means you have many wavelengths. But what we use here is mostly monochromatic radiation. You have one particular wavelength. So mostly coming from copper, K alpha, So if you use monochromatic, there are two ways of looking at. You can directly look at some single crystal materials, or you can do we talk about single crystal versus polycrystals, right? If you have a single crystal, that means you have one particular crystal, right? So that you can study with some monochromatic light. So, but it doesn't do much because you have only that interesting plane is exposed to this light, right? Suppose if we have silicon 111, so then you see one peak corresponding to that 111, right? Because other planes are not exposed. If I want to expose other things, what should I do? I can take this crystal and make it a powder. If I do powder, even other planes are exposed to this light, right? So that's what we call so this powder diffraction. Later we'll talk about that one. Typically, if you have a monochromatic, we can look at single crystal method, or something called the divide. This is mostly used for the single crystals. But if I have a polycrystalline sample, remember we talked about something that is not single crystalline. They have different crystalline material. So that you can study with this monochromatic light. That's easy, right? Then actually you are going to see some kind of rings. So we'll talk about all these things later. Typically we call this is single crystal method, and this is called the Debye-Scherrer method. So Debye-Scherrer means you are looking at polycrystal material using a monochromatic X-ray. So then this single crystal you can also look at with different wavelengths. That's interesting, right? Because then that method is called the Laue method. Actually, that's how first Laue saw that crystal structure. He exposed this some single crystal for different lights. He saw these different spots on the photographic film. So here, that's the Laue method. So what he has is one single crystal, but you are using different lambdas. Even if it is a single crystal, you can see different features because this has different lambdas. Yeah.
Does it matter like how different? So
No. So depending on that difference, you get that different spacing.
Okay.
Yeah, but you cannot make two different lambdas because you are. I will explain how you make the X-rays. Yeah. So then Debye-Scherrer, that means you are using single radiation, but you are looking at polycrystalline. So that means you are getting, because this one now has this kind of, right? From this one you get this kind of cone here. Then from the other part you get another ring like that. If you have polycrystal samples, what you are seeing is rings. So if you see this kind of if you have polycrystal samples, basically you are seeing some kind of rings. If you have a single crystal, basically you are seeing some kind of. So if you have polycrystalline, your single crystal with different wavelengths, that also you will see some this kind of rings. So if you make some sample, if you have some kind of crystalline plane, what we usually do is we just grind it to make a powder, then look at the one with single monochromatic light. Then you will see many planes, right? You will see, we can say it's 100 or 111 or 420, this kind of peaks. If you have one, if you give me one, say, single, like a wafer, If I do this one, you will only see that particular direction, right? That's why typically we do something called the powder diffraction. So typical X-ray diffractiometer you may have seen. What you have is, typically you have X-ray source, then you have some kind of aperture to pass the X-ray, then you have a sample mounted here, then you can rotate your sample, and also detector, also we call the goniometer, this one, right? It can be rotated here, then you can catch all the angles, so then the intensity is coming from each angle can be measured. That's what usually we do, 2 theta versus your intensity. We'll try to analyze this one. Also, it's very important in X-rays, you are typically talking about this angle 2 theta, because you have X-ray coming like this. This is my X-ray, right? So, angle always we measure from the sample. Please remember that. In optics, remember, we always measure the angle from the normal, right? If somebody is working in optics, typically these are the angles, right? Measure. But in X-ray, we are usually measuring from the sample. That means if you have this one, this is the outgoing. What is the change of the angle? 2 theta, right? It's coming this way and moving this way. That means this angle is, this is 2 theta. So typically if you look at any X-ray, your x-axis is usually 2 theta. That's what you are measuring. Directly you can measure that one, right? From the initial direction, how much it is deviated, right? That's why any place you will see, you can see this was coming like this. Now it is deviated by 2 theta here. Okay, so how do you generate X-rays? Anybody remember? To generate electrons, you have to have some high energy electron incident on some metal, right? So metal can be anything like the typically in ours we use copper. So you can have any of these metals. So then what happens? These electrons are going to get stopped, right? Then you have some kind of radiation coming here. Then at high enough energies, the electrons in this target material, they are going to be excited, right? So then from excited state, when they come back to your ground state, they emit something called the X-rays, right? So that's basically, so you can see electron beam. How do you make electrons usually? Electron beam, there are several ways, right? One is heat it, right? We call the thermionic emission. If we have a filament, if you pass a very high current, you are like emitting electrons. So, but this has to be done in a vacuum, right? Otherwise, electron cannot go anywhere. We call the thermionic emission. Another one is apply very large voltage. We call the field emission. That's what, remember, old days your TV was so big, where they had the cathode ray tube, right? You have to apply something like kilovolt potential to make that electron to pass through. So that's called the field emission. So another way is photo emission, right? If you shine high energetic light, you can make the, but that's not very practical. Typically, you can have either field emission or thermionic emission. If you go to any of these scanning electron microscope or the transmission electron microscope, in old days everything was thermionic, but nowadays they have field emission, FESCM, FETEM, like the field emission. But nowadays you can do that one at low enough voltages. So X-rays, if you look at typical X-ray, wavelengths are in the angstrom range, right? Yeah, here wavelengths are 10 to the power minus 10, typical X-rays, but if you go to like very hard X-rays, it can be even smaller wavelength. So this is a wavelength, how wavelength increasing. That means energy is much higher here, right? So, that's compared to other like infrared, microwaves, radio waves, X-rays are so only smaller than cosmic rays, so other gamma rays. So this is how X-ray happen. So if you have some high energetic electrons coming, so if you have a target, so they are going to stop. That's why you see this kind of emission spectrum. But at high enough energies, you are going to see this. So what are these things? That's basically, if I have these electrons, right? So you have these electrons, these are the valence electrons. Now I have this electron beam coming, right? High energetic electron. They are going to knock out one of these inner co-electrons, right? So then this is at much lower energy, but these are at higher energies. They are going to fill this empty electron, right? So this is higher, this is lower, then you have energy difference. So that delta E will be some, this light is going to be, so what is that? That's the X-ray, right? So you can have it's coming from say K, L, M, N, any of these orbitals, right? So typically, if you have something coming from L to K, that radiation coming here is called the K alpha radiation. If it is coming from maybe M to K, so if this electron is going to come down here and emit electrons, that can be that K beta. This wavelength, this is energy increase in this way, right? So this is K alpha, K beta. So typically, I think everybody remember this one, right? Your orbital K, L, M, N. Each one has, K has only S orbitals, L has S and P, M has this L equals 1, 0, 1 and 2, right? Everybody remembers PDF on these things. So it's how energies are transferred. So that's how you get the K alpha and K beta. So typical experiments in our setups, we are using K alpha radiation that is about like 0.6, about 0.8, 7 some angstrom wavelength. So also you can use molybdenum ones here. I just explain what are these two radiations. K alpha is this one, this high energy, right? Because this is wavelength. High wavelength means lower energy. Okay, so that's basically, so this is also we talked about. Okay, so now if you look at diffraction theory, any of these photons, right? So what are we studying? So basically, suppose I have these crystalline planes, right? So we know, suppose this is some DHKL, so some planes, right? So suppose this plane is some HKL indices. Everybody remember this? That's the plane, right? So that means we know how to calculate the space in between these planes. It's very easy to calculate, actually that we are going to do later. It's easy to calculate for cubic crystals, right? So typically D is given by A divided by plus A square plus L square. Don't worry about that right now. So later we are going to, but this is the simplest case, cubic one. But if it is hexagonal, different. In the homework I asked you to do for the hexagonal one, right? So then you have L. It's very simple, right? So if you can write this one, your reciprocal, this B1, B2, in terms of these unit vectors. So then we know how to write G, right? G is given by H B1, K B2, L B3, right? So then we know how to write B1, B2, 3 in terms of X, Y. If you do this one, what you get is something X, something Y, something C. So then what is your the this one is b, this square plus this square plus this square root, right? Then also we learn this is given by nothing but 2 pi over DHK, right? So from there you can calculate DHK. Very simple is so now in this case, now you can see this is my HKL plane, right? So now I have to look at this X-ray. So this X-ray coming here and getting reflected by this plane here, the top plane. Then also this one can come through and get reflected from this plane, right? Now look at these two waves getting interfered here, right? Two waves coming together, they are going to interfere. So we also know the path length between these two rays determines whether they are going to interfere. We call the constructivity or destructivity, right? So one thing to remember is, if you have the path length, say that is delta, say x or delta r. If this path length is integer number of lambda, this is typically constructive. If this is half lambda, that means this can be like lambda, 2 lambda, 3 lambda, like that, right? Here if it is like lambda by 2 or 3 lambda by 2 or 5 lambda by 2, this will be, we call the destructive interference. So either this way or in terms of this we call the path length. So also we can define something called the phase path difference, right? Yeah. Then also we can think about the phase difference. How do you define the phase difference? Typically we define phase difference as a delta pi. Actually that is 2 pi over lambda times your that path difference. Everybody should remember this relationship. How phase difference is related to path difference. Because 2 pi means lambda, right? Just imagine this one. If I go from here to here, this here, right? When I come here, it is like this. If I come here, that is like this. If I come back here, so this lambda, right?
Yes.
So how much here is 2 pi, right? 2 pi means lambda, right? Then you can get what is this. So if you get constructive interference if this phase difference is the even number. So that means 2n times pi. Or this is a constructive interference, or this is odd number, that means 2n plus 1 times pi. This will be destructive interference. You get the same answer, right? You can see here 2 cancel, you get pi also cancel, delta R equals n lambda here, right? Here, if you take 2 pi over lambda times delta R, you can see pi cancel, then delta R equals what? Lambda times 2n plus 1 divided by 2 means n plus half, right? So, same thing. You get the idea. So you have to remember either this way or this way, whatever it is. So now in this case, suppose these two rays are coming, right? So if you look at this one, up to this point, they both go the same distance, right? So from here to here, also they go same distance. Only this much length is more compared to this one, right? So this one is going through this much additional path compared to this one. That means the path difference between this red one and green one is basically this distance, right? So up to here is the same. From here it is same. This is the extra length, right? So that means your path difference is what? Suppose this is my D, that is DHK, right? So that we talk about this one. So that is this D. So then I can write this distance is what? If this angle is, because we are talking about this angle, right? So if this is theta, this is 90 minus theta, this is theta, right? So this is theta, then we know this is also theta. Then this length is this 90 degrees, then d sine theta. Here again also this is also d sine theta. Then the path difference is 2d sine theta, right? 2d sine theta. So if we want interference constructively, this should be simply n times lambda. That's it. Okay, so that's basically. So this is basically DHKL. If you want that, you can find DHKL is basically nothing but 2 pi over this GHKL. This one, right? So you can calculate that one for anything. So please remember this is the most, I think, general equation. If you want to see the diffraction, you need to satisfy this 2d sine theta equals n lambda relationship. So this is called the Bragg's law. So any crystallography, when you try to interpret your data, you have to use this equation. Also you have to be careful. Let's do one quick example. Suppose if you use a diffraction coming from aluminum, so using X-ray that has wavelength 0.7, that's actually mostly the copper K alpha wavelength. The second order Bragg diffraction, what does that mean? 2d sine theta equals n lambda, n is 2 now. That's the second order one. 2d sine theta equals n lambda. In this case now this is 2 times, so n equal, so that's the second order. So then you have to find also this, like I said, typically they give 2 theta. Then theta is half of this one, right? So that means you have 2d sine, that should be 10 plus 1. So please remember, when I give some homework problem also, mostly I give 2 theta, but you have to use theta. So from here you can calculate lambda is known, you can calculate d. So then also this is aluminum. So anybody remember aluminum, what is the crystal structure? Aluminum usually FCC structure, but still is a cubic structure, right? So that means you can use, so d equals a over this one. But in this problem actually they are asking, this is given for this plane 1, 0, 0 plane, any of these planes. So that means your d, any of these plane, so only 2 terms are zeros, right? So that means your d equals a, right? Because this is 1, this is 0, 0, then your d equals a. That's what this problem is about. You calculate d, so that's the same as your a. A is the lattice constant, the between distance between 2 lattice points. So then also you have to be careful what you are really measuring. Suppose if you have this diffraction due to these two rays, so 1 prime and 2 prime, in that case, so this is your distance, right? Suppose this is, we call 1, 0, 0. So then you can write your equation as 2d 1, 0, 0 sine, this one equals, suppose this is the first order. So now if you have diffraction coming from this plane, so now we are talking about diffraction happening from 1 prime, 3 prime. In that case, what is your separation? Only this much, right? That is actually 2, 0, 0 plane. Remember, this is 1, so this is half, right? So that means when you take the reciprocal, this becomes 2, 0, 0. In that case, your equation should be, because you have different angle now, right? So we have to be careful how you look at from which plane you are getting the diffraction. That's why when you have this powder sample, you get all these peaks. Okay, so now we are going to go to the real diffraction theory. This may sound a little bit complicated, but I just want you to understand the final results, but I like to derive that diffraction theory. So when you talk about the diffraction theory, there are very important two factors for a given material. Something called the structure factor and the atomic form factor. Structure factor means if you take some material, suppose in a unit cell, right? You have these are lattice points. Then I'm going to put my basis into this one, right? Suppose my basis can be this one and suppose this one, right? That is my crystal. So then the diffraction, we talk about diffraction, either diffraction, this pattern as spots here, and also some intensity, right? You have seen like some are very bright, some are little bright, or in terms of this way, maybe this is like this like this. So that means there are two things, right? One is the location of this peak, other one is the intensity of the peak. So typically the location is governed by your crystal symmetry. Suppose also your crystal dimensions, right? Basically A, B, C and alpha, beta, gamma, right? That determines your crystal structure, right? If they all are equal, they all are 90 degrees, you have the cubic. If they are all non-equal, they all are 90, you have the orthorhombic, and you know how, right? So all these different Bravais lattices. So typically we are looking at these reflections coming from these different planes, right? So because this is your lattice, but mostly we are talking about what is happening from the crystal planes. Right? So then if you take this atom here, right, in the basis, this atom has electrons, right? Suppose this one also has electrons. That means we need to know what is the electron configuration, or that electron count of each atom. So that is given by the atomic form factor. Atomic form factor tells you how the charges are spread at that atom. So that means the intensity is mostly governed by the atomic nature of that atom. So that's what. So what we are going to do is in this class, so we want to, this is my sample. I am going to expose this sample to some X-ray source, right? So then this has some charge distribution, right? That's the material. So that's all the electrons and everything. We define something called the charge density, rho r. That rho r can be different at different positions, right? So that rho r is going to determine how they are going to be scattered. So eventually what you want to calculate is what is the intensity of that scattered light at this point. That's all we are going to do. That's a little bit, it's not bad. So we have wave coming here. You know how to write a wave, right? How do you write the wave? Everybody should know the wave equation. These are very simple. Typically we write, mostly we talk about linearly polarized light, or any general wave you can write as, anybody remember this one? Minus, if you want, minus omega t if you have the time dependence part. This is not relevant for this one, right? So k is the direction of that propagation, r is for any distance from that one. So if you know this one, you can calculate what is the intensity of light coming at this point. This is all you need to remember. Everybody familiar with this one? So the k is basically 2 pi over lambda, right? But this can be really complicated if you have like something called the circularly polarized or elliptically polarized light. But here we are mostly going to consider linearly polarized light. So that should be easy. So like I said, you have to consider these two things. So this is the one I was talking about. The position of the diffraction spots or the position of these angles, they are mostly determined by your crystal lattice, right? So the intensity of the spot is determined by that basis of the atom and how its electrons are distributed. Then also we talk about these diffraction spots, the distance, they all coming from the reciprocal space, right? G is determining the everything, right, in the reciprocal space. What we are seeing on this photographic film is basically reciprocal space property. If you look at the optical microscope through your objective, what you are seeing is real space property, right? But if you have some electron diffraction, so that's basically we are looking at these are all in the K space or the reciprocal space. Okay, let's derive this equation. So, before that, yeah, very simple two things I want to talk about. Remember we talked about the what is called the elastic versus elastic scattering. Elastic scattering means if we have some, so if I have some wave coming here, suppose my wave fronts are like this, right? Wave is coming with some wavelength, say K0, right? So now this is my sample, so this is going to be diffracted, right? Now it is going with, these are my wave fronts, this is going with some K. So then what is the, if I have this, suppose this vector is R, then what is the path difference? Basically if I put my 90 degrees here and 90 degrees here, basically this is my path difference, right? That we already calculated. In real terms, actually you can write this one. What is this length? It's basically if you have K0, if you take the dot product with my R and divide by unit vector, right? K0, this is this length. You can easily show that one. Like I said, if you want to take, if this angle is pi, what is this distance? R sine pi, okay? So if you can write this one in terms of K0, you can show this is K0 dot R is what? R is this one, K0 is coming in this one. This angle is really 90 cosine 90 minus pi, right? That is sine pi. You can easily show that one. This length is K dot R divided by the unit vector in that K direction. So that's what this one. You can easily show that one. So, but to make this simple, I just draw this way. Suppose this is my sample. Suppose my planes are like this or something. I have K0 coming like this. This is my wave. So then I have this one going like this. This is say K. So if they are elastic, that means your K0 and K has the same magnitude, right? Because K is basically 2 pi over lambda, right? Your lambda doesn't change, right, due to the diffraction. So now what is the difference in K? Delta K. Delta K is basically K minus K0, right? Delta K is K minus K0. How do you calculate that? K minus K0 means this is, we just draw this way, right? Then that will be this one. K minus K0, with this K0, this is minus K0, right? If you add these two, K minus K0, this is your delta K. Is that clear? So also we know this length and this length are same. So this is my theta, this is theta, that means this is theta, this is theta. That means delta k is what? The magnitude of delta k is k times sine theta. You have two of them, right? 2 k or k0, magnitude is the same, sine theta. That is delta k. Isn't it? So you can see here, your delta k is, this is k and k prime or whatever. So this is k0 and k. So your difference will be simply 2k sine theta. But this is really interesting. Now, do you see something here? This is delta k, right? That delta k is normal to your crystal. Do you remember something normal to your HKL plane? G, right? G is always. So in last lecture we talked about if you have HKL planes here, your G vector is always normal to this HKL plane, right? So then what do you think about the delta k and G? They should be the same thing. We know delta k also inverse wavelength, right? G also inverse real space, right? So that means later I am going to show you that delta k and G are exactly the same thing. So actually later we can say delta k and G, if you say delta k and G is HKL, this is another way to say the Bragg's law. So you can easily get that relationship from this. Remember, Bragg's law was 2D sine theta equals n lambda, right? So from here you can get that equation easily, right? If you write this one as G, so see whether you can get that relationship. That's easy, right? Actually, I'm going to show that one. Delta k is 2k0 sine theta, right? K is what? 2 pi over lambda, right? Times sine theta equals, if I write G, G is what? G is typically 2 pi over D, HK. What do you get here? 2 pi cancel. What you get is 2d sine theta equals lambda. You get the same answer, right? 2d HKL sine theta equals lambda comes. Yes, get the same answer, right? So we'll show this one later. But what I'm going to say is this delta is nothing but actually G. Okay, now let's think about this scattering from electron. So this is really important, right? Suppose if you have one electron, so here have this one electron, so you have X-ray beam coming, what will happen? This electron beam has, that's electromagnetic wave, right? You have electric field and magnetic field. It's a transverse beam, right? So that beam is going to get scattered due from one electron, right? Why is it going to get scattered? You know, this electron is actually vibrating, right? So because of that, this electric field is going to be interacted with that vibration. You get this one. Anyway, just think about electron beam scattered from one electron, right? So then if I have two electrons, again same thing, right? I have one electron here, one electron here, you get two beams scattered from two electrons. But if you have atom, you have many electrons, right? So typically if you take an atom, so here we just talk about just one and no two. But if you take electron from nuclear, you can see lot of electrons, right? These are like electron cloud. So that means that X-ray beam is going to get scattered from all these electrons, right? So that's why it's getting a little complicated, right? That's why we define this whole atom with some charge density rho r. So the rho depends on the distance, right? So that's what, but this is still from one atom. Just imagine if we have lattice with how many atoms? You have many atoms, right? So this is, if you have lattice, each lattice point has a one basis atom. So that means you have many atoms. So that means this electron is going to get scattered from that entire atom. But each atom has that large rho r distribution. That's also not the case. Then you have, suppose if you have three-dimensional crystal, not just one, right? Then you are getting this three-dimensionally scattered light coming, right? So that means if you consider this large sample, you have to consider that X-ray getting scattered by all the atoms. Each atom has that lot of electrons with the electron distribution. You can see how complicated it can be, right? So then how do we tackle this problem? Can you consider scattering happening from all the sample? What can you do? You just consider one unit cell. Okay? You just consider one unit cell. That unit cell has your basis atoms, right? You just consider only the scattering happening from one unit cell, then you can expand it to the entire crystal. That's the whole approach. So this is what we are going to do, scattering by a unit cell. If you consider unit cell, you have origin, then you have, suppose this is a 3-atom basis, right? You just only consider happening from this each atom. But we know how to calculate from each atom. That's also complicated, right? So that's the approach. Typically, you only consider one unit cell contribution. Okay, now let's consider this formalism. So, like I said, I have X-ray source. Suppose this is your wave. So that has your wave vector k0. So it is, suppose if it is incident here. So now this wave is going to kind of agitate the entire sample, right? From that, every point of this crystal you are going to have X-rays coming from each point. So that means you just consider some general point from here to here R, then calculate what is your intensity at this point. So then you have to integrate all over R to consider the entire crystal. That's it. It's not very difficult. So suppose here, suppose my intensity is say AP at this point, then what is the intensity at this point? So if intensity of the light starting from this point, I will call this AP. Then what I want to calculate is what is the intensity at this point B. I want to calculate X-ray scattered, the red light coming here. Suppose that has your vector K. So that K and K0, they have same magnitude, right? They are elastically scattered. Then I can write this AB as very simply AP times EI. That K is the vector, right? This is my K dot R is now from here to here, coming from here to here, right? That is going to be R prime minus R. So this is K dot R prime minus R. Then I will not try to omega t terms, so that doesn't count here. Yeah, even here they don't write it, right? So here, please remember, we measure everything. This is my origin. I measure everything from here because later I want to integrate over R. Is that clear? So that means but the wave is coming from here, then my vector here should be this one r prime minus r, but this vector we write as r prime to this point. This is my origin. This is we write as r. Is this clear for everybody? But this is also we have to multiply by the small area. Suppose it's coming from this area. This is r vector. This has a charge density rho r. That means I have to multiply this by rho r. So that means if we want to calculate the entire thing, I have to integrate all over r. So now AP, what is AP now? This one is excited due to this X-ray, right? I can write AP as, actually A0 is coming from this one times, I can write that AP as some initial intensity times EI K dot, this is my K dot, times this point is basically R plus R. This is K0 R plus R. Because that is, because we are measuring everything from this origin here. Is that clear for that one? So omega t terms, so we don't care about that one. So that's it. Now plug in that AP here. So then what you get? You have, it's not very difficult. So if you do that one, what you have is AB becomes, AP I can write as A0, that's a constant, EI K0 dot R plus R, I will not write omega t, then I have rho R here, then I have EI K dot R prime minus R. That's it. So now if you take everything in R, I can write as EI, I have K0 R, here I have minus K dot R, right? Or I can write minus I, K minus K0, doesn't matter. K minus K0. If I put minus here, then I have rho R. That's the only thing that has R dependence. Everything else, I have this all EI K0 dot R. Then I have here EI K dot R prime. So they don't have any R dependence, right? So now if I want to do the integral, so basically what is important is I have to integrate all over R. That's it. So this is all constants, right? So then A at this point is proportional to, so I can write this one as AB is proportional to something called E minus I. I can write this one as delta K, right? Delta K dot R times rho R times dq. That's it. So here, do this one. That's what important thing here. A at this point, due to this scattering of this light, I can write as rho R. Rho R is the electron density of this sample. E minus I, this is your delta K dq. Anybody understand this? What is this one? This is basically Fourier transform, right? If you can write like rho K, delta K kind of thing. Okay. So, yeah, please remember this one. So what we get is, if you can start from here, your I is given by simply this one, then that's a function of delta K, right? So what is that's the amplitude I wrote. The intensity is what? Typically square of that one, right? So remember, intensity is given as your amplitude times a star or a square, right? So that is the intensity rho r, this one. Now you can see, ideally, what is this delta K? That becomes G. So now you should remember what we learned before. Rho r times E minus G dot r. You remember from previous class? We defined actually how the Fourier transform of your rho function. So anyways, if you don't remember this, so delta K is fine. So the diffracted density is the basically Fourier transform of your electron density. That's what you have to remember. So this is the basic idea. This intensity is nothing but, so if you don't follow this one, don't worry. So what I mean is the final answer. But my intensity is basically Fourier transform of your rho r. So what is Fourier transform? Usually you write as E minus I some K dot r or G dot r. Remember we did this one before. Times d cube r. That's the Fourier transform. Okay? So but in this case here we have delta K. So later I am going to show delta K is nothing but G. So your intensity is proportional to square of your Fourier transform. Sometimes you can write this one as rho delta K. That's fine, right? This is the Fourier transform. So everybody familiar with Fourier transform? Rho delta K is basically rho r E minus I delta K dot r e cube r, right? That's the Fourier transform. So diffracted intensity is the square of the Fourier transform of the electron density rho r. So here this is what we did before. If you remember, since these your lattice points are translationally invariant, we wrote this way, right? Because of this we could write G in terms of G, then we got this relationship. Everybody remember this? G dot this reciprocal space translational vector, real space, yeah, 2 pi times M, right? That's how we define all this B1, B2, B3 things. Yeah, here it is, same thing I just write. So now you have to, so this is what we did in the previous class. Well, you can go through this one by substituting and doing the integrals, so using the delta functions. So I don't know how much you are familiar with the integrals of delta function. Anybody remember x minus alpha? What's the delta function? Typically ei x minus alpha times p dp, right? That's the definition of a delta function, right? So if you can, also anybody remember this integral of a delta function? If you have some fx, if I integrate x minus alpha, what is the answer? This simply f alpha, right? So these two you can easily write, because if you look at this one, so this is how we wrote because of the periodicity thing, right? So if you plug in this rho r here, then you get this equation. So now if you look at this one, this is nothing but this equation. That's a delta function, right? Anybody understand this one? That's a delta function, right? ei x minus alpha times dp. This means basically delta function. If you put this one, if you integrate, then you get the answer when g equals delta k, right? Because x equals alpha. If you plot that one, you get I delta k is basically rho g. Rho g is what? Fourier transform of your electron density. That's it. So anyway, just forget everything if you don't follow this one. I just want you to understand this one. Your scattered light intensity is given by square of your Fourier transform of your square of the Fourier transform of your electron density. What is rho g? Rho g is basically rho r e minus I g dot r e. Please remember this one. Okay, that's all I want to show. Then we can use this one. Yeah. So this delta k equal g means that's basically we already showed this one, right? Yeah. Just remind you these things. So this is we already showed this one, how that is going to give you 2d sine theta equals lambda. Okay, that's all. So now let's. So is that clear for everybody? So almost time. So then in next class we will use this relationship to calculate your structure factor. That's very simple. So I want to calculate structure factor for all the lattices. So please don't worry too much if you don't follow that derivation. But that final equation is the important thing. Your intensity of the scattered light is basically square of the Fourier transform of your electron density, right? Rho g. That's all we need to know. Okay, I'll see you Thursday. Thursday is basically apply this one.